Ladies and gentlemen, good morning. Welcome to the fifth lecture of this course, Quantum Transport. And today we will have yet another change of the topic. Till now, we've been dealing with electron waves without interaction, scattering approach. We have looked at different facets of this. The case of few channels, the case of many channels, where Ohm's law is restored, but still the system remains quantum. And now we switch to interaction problems. It's worth saying that in solid state, interaction of electrons is very complex and rather incomprehensive topic. One could not really exactly solve even a simplest model involving interaction. And yeah, you cannot teach it. Of course, the researchers know the answers, which have been obtained by combination of different methods and approximations. Still, electrons with correlations with interaction remain a kind of active research topic in solid state. However, as you probably remember, in your course of solid state physics, there was almost no interaction just because it is rather complex. Strangely enough, if we go to quantum transport, interaction has a very simple facet. I would say even primitive. People kind of were very much surprised and fascinated how primitive, but yet interesting it is. Right. And this aspect of interaction electrons is called Coulomb Blockade. As usual, the names, the terms are the most complex subject. It's difficult to explain how do they come about, but I will do this in a slide or two. Right. Sure, what will it be about? First, I will call what in general about charge quantization. Yeah. Number of particles is discrete. Particles bear elementary charge, so the charge must be quantized, even in large systems. And I will talk about charge and energy, the energy which you have to pay for charge and which describes interaction. In this context, we will talk about islands where charge is stored and barriers which separate islands from metals to provide isolation to store discrete charges. Good. Very soon we will go to devices because, well, quantum transport is basically all about devices. And we will concentrate on what we call single electron transistor, where electrons will go from one lead to another lead, hopping through this Coulomb island, hopping through interaction region. And we will look at manifestation. We will look at the method with which we can describe transport. That's very general method. It's a master equation, probability balance. We will determine tunneling rates in the presence of Coulomb blockade. And right, in the end, I will talk about some strange process which exists only in quantum mechanics, where two electrons kind of cooperate and hop together. That's the plan for today. Let's see. I kind of, to be very frank, there's less participants than I usually have. Wonder. Okay, 11 participants. That's okay. I also wanted to say that on coming Wednesday, we will have, how to shall I say, explanation or homework session. As you remember, you get homework. You're kind of not forced to do this. We won't check this homework, but we will explain this. So a week ago, sir, I believe I gave you the homework problems to look at it. So what was the catch about this? First of all, homework problems are kind of similar to some extent to actual exam problems. Something like that will come during examination. But it's not the only purpose of homework. It is also that we want to, I would say, smuggle some extra information which we don't have time to put into the lectures. Right, sir. The present homework is a mixture of these two. It is decisively, in most cases, more complex what you get at the examination, but you know, for exercises, it's better to make it more complex than in real life. Fine. If you have any questions concerning homework and the session on, let's see, Tuesday, please shoot. Let's see, I guess I have a question. I couldn't find the homework at the given link. I don't know, Francesca. Oh, that's interesting. Let me check during the break whether it went well. All right, I will check it during the break. Good. And let me get back to Coulomb Blockade. Right. First of all, I would like to talk about charge quantization and charge and energy, which comes almost immediately. Right. So let me consider a metallic island, and it doesn't matter really what size it has. Let me consider a metallic island which is isolated from anything. It hangs somewhere in vacuum. Right. And my statement, which is actually might look a bit strange, but nevertheless, if you think about this, it's certainly true, is the charge in this island is quantized. Why is it so? The island is isolated. The overall number of particles which is in this island is integer and constant. So there is some excess of electrons above protons. There is some charge, and this charge is discrete because there's discrete number of particles in this particular island. Right, there could be zillion of protons in this island and zillion plus one electron, so one can see this excess charge. How? What is the manifestation? Right, first of all, let us recall that in a metal, we don't have electric field, we don't have charges in the bulk. What happens to this charge? In one way or another, it is distributed along the surface of this island. It is distributed along the surface, it's there, so this charge produces electric field, in this case in the vacuum which surrounds the island. Yes, since there is an electric field costs energy. There is energy density proportional to the square root of electric field. If you go back to your electromagnetism course, you recall that this is called capacitive energy. So a capacitance can be associated with this island, and the energy which is accumulated in this electric field is Q squared charge divided by 2C. It's a formula for energy of a capacitor. So we substitute here number of excess electrons times electric charge, and we have charging energy. Some scale, EC, which is E squared divided by 2 capacitance, times number of excess, squared of excess electrons. So there is some energy which, for instance, has to be paid if we want to charge this island. Let us figure out how big this energy can be, and let us compare it with other energy scale which can arise in isolated island. So since island is isolated, then we recall quantum mechanics, then the spectrum of electronic states in this island is discrete. So there's plenty of levels which are separated by some typical energy delta level splitting. Good, let us estimate these two energies for some circumstances, and we also train in making estimations. Never hurts. So let us take an island which has, say, cubic shape with a length of 100 nanometers. So that's pretty big. You cannot see it with an eye, but yeah, you can easily fabricate such elements. Good. What's number of atoms? Atoms are spaced by roughly 0.1 nanometer, 1 angstrom. So we conclude that there are 10 to the 9 atoms in the island. Let us estimate level spacing. We usually have 1, 2, 3 electrons per atom. So we have roughly 10 to the 9 electrons. These electrons are in a band of the order of Fermi energy. Typical Fermi energy is 10 electron volts. Right, so I divided by number of electrons, which is number of atoms. I got 10 to the minus 8 electron volts. That's the spacing. If I would estimate the charging energy, I could think of capacitance, but it's simpler to think about the two. Instead of this charge distribution, I would just take distribution of this sort. Two charges which are separated by a typical distance L. Then I imply I implement Coulomb law for this interaction, so the energy would be E squared divided by L. Right, again, it is good to measure it in atomic units. For atoms, this scale would be 10 electron volts as well, because atoms kind of roughly composed of the same kinetic and potential energy. Right, and L we can estimate as this, or alternatively in atomic units you can take number of atoms to the power 1/3. Good. If we do this calculation, we come up with 1 milli electron volt, which is indeed a typical scale for most Coulomb blockade phenomena observed in quantum transport. 1 milli electron volt. Good. Then what we can say, we understand that charging energy is a way more important than level spacing than kinetic energy. It is something what we don't usually hear in solid state physics. Yeah? In solid state physics, you kind of tend to disregard charge interaction and related charging energies, but you understand that it's impossible if you really think of if you really depart from electron neutrality of your material. In this case, there will be always charging energy which will greatly exceed the spacing, level spacing in your quantum system. Right, now let me understand why it is Coulomb blockade. So Coulomb is because of Coulomb law, electrostatic energy. Blocking comes from the fact that if this charging energy is not available, it can come from external voltage source, it can come from temperature. If this energy is not available, then you just cannot put anything into this island. This process is blocked, right? That's why it is called blockade. Fine. Let me go on. And as it is usual in quantum transport, we better talk about some devices, simple devices, which allows you to get what is it about. So let us introduce a simplest device, which is called single electron box. That the function of this device is very simple. It is to keep and change a discrete charge in this island. To change this, one should have some source of electrons nearby. Here it is. So there is a bulk metal which is close to the island, and there are some tunnel connections. We will specify further how intensive this connection has to be. So electrons can tunnel from metal to island and back. Right. To control the charge, we implement a gate electrode. So there is a gate electrode, and there is no connection, electric connection between island to the gate. However, there is electrostatic connection. If we keep voltage difference between metal and gate, what will happen? There will be some electric field between metal and the gate. And this electric field would like to push charges to the island or repel charges from the island. Is this point clear? Okay, intuitively is clear, and now we want to quantify this. Right, and to this end, we need to solve the following electrostatic problem. Okay, so it's a simple capacitive circuit. What we have here, here's a metal which is grounded. Here's a capacitance between islands and metal. And here's a capacitance between island and the gate. Fine. Then we compute electrostatic energy to come with the following expression. So what is there? First, it's overall energy scale, charging energy, which is in this case E squared divided by the sum of two capacitances. And one finds n squared. But in addition to n squared, there is some combination of letters. What is this? It is called in electrostatics, again, induced charge. This charge is not discrete. It's just per function, linear function of gate voltage. It shows how much charge would be in the island if the charge is not quantized. All right? So the gate wants to set some continuous charge into the island. And in that case, the energy would be minimum. That cannot happen because the charge is discrete. To understand what's going on, let us plot this energy. Let's take this energy and let's plot it versus gate voltage for different fixed ends, right? Each curve of this kind is a parabolic curve, which with the bottom at 0. And right, we see parabolas of different color. If I want to understand the ground state, the most favorable, the most energetically favorable state, I need to connect lowermost pieces of this parabola. That's a spiky curve which I have. All right, and anytime it has a spike, look what happens. The most energetically favorable value of n changes. So the island gave into what gate requires, but it does it in discrete steps. So now I have this picture, number of excess electrons versus gate voltage. It's staircase. So increase gate voltage and step by step you increase the discrete charge. You can also decrease it if you apply voltage of different polarity. So there will be less electrons and protons. There will be effective deficiency of electrons. So since we cannot repel all electrons from the metal, it would be disastrous. So that's a curve with great accuracy, absolutely symmetric with respect to 0. Good. That's single electron box, a device where we can control electric charge. Any questions so far? It's not the case, so let me talk more about how we make this system in practice. We will talk a little bit about semiconducting quantum dots, but here I would like to concentrate on metallic systems. And let me just describe some simple technology with which you can make a Coulomb blockade systems. Right. It is, say, we have a substrate and we have means to evaporate thin metallic films onto this substrate. And it's goes like this. First of all, we make lids here and here. There must be some mask which makes the gap between these two lids. Right, there are means of electronic lithography. Fine, so we have these lids. Then we let them oxidize. One could put oxygen to chamber or whatever, just wait. And these lids will be covered by oxide. And under them, we put this short piece, island, which will overlap the lids. Good. That's how first Coulomb blockade systems have been done, and this technology still exists and works. What will happen if I look at side view? So there will be the lead, which we deposited in the first step, then oxide. And above this, we will have the islands. It's called overlap tunnel junction. Now I wonder how strong should be this tunneling barrier, or how resistive it is. If it's very resistive, then there will be no electric transfer. It's very easy to arrange such an insulation that electron transfers would happen once in a week, which is not really suitable for any experiment. If you make this connection to stone, you form a shortcut. So there will be metal and some shortcut to metallic island. But in this case, the metallic island will become a part of the metal, and you can't really have integer number of electrons. There's no space for charge quantization. So there has to be some compromise, and it is a funny estimation for this compromise, which is kind of half classical, half quantum. Let us treat this island as a simple classical electric circuit. So there is some resistance associated with this tunnel barrier and some capacitance on the island. And from this, we can get a typical time which is required to touch or detach this island. This is called RC time in theory of electric circuits. Right, okay, that's a simple classical estimation. Let's go quantum. Let us implement Heisenberg uncertainty relation. So there is some energy, which is charging energy related to the charge, and some time, typical time of this discharge. And to have a kind of certain energy, this time, according to Heisenberg, must be sufficiently long. How long this product, energy times time, should exceed Planck constant by at least several times. Very good. Let us substitute what we have. So this is, instead of delta E, we have charging energy. Instead of time, we have RC. And then capacitance just drop out from this estimation. And we conclude that in order to have well-defined charging energy, in order to have well-defined isolation of an island, the resistance between the island and the source or drain should exceed this ratio, resistance quantum. But it's just the same as the conductance upon a factor, just the same conductance quantum, which we have encountered in scattering problem. So it comes here again, and it has a value of a couple of like 25 kilo ohms, something like that. So that sets the scale of the resistance, which can be implemented in Coulomb blockade circuits. Very good. That is the condition on the resistance. There are also conditions to see Coulomb blockade conditions on temperature and voltage. That's about energy supply. If temperature is much bigger than charging energy, then yeah, you can easily charge and discharge this island just by means of thermal fluctuations. Or you could do the same with voltages which you apply to the circuit. So bus quantities must be smaller than charging energy. Fine. We have described the conditions, and now we can go to finer details. And we will talk about single electron transistor. Here I sketched capacitive circuit. Perhaps I want to supplement it with a kind of simple drawing. So what we have here are leads. We have an island with overlap junctions, and we need some other electrodes to control the charge. Let me put it somewhere. So that will be gate. So how does it look like in the language of electrostatic circuits? The island with discrete number of charges is eventually here. All right, there are capacitances to the gate, to the left lead, to the right lead. Right? Leads are energized by voltage sources. And there's also a separate voltage source for the gate. So we have generally 3 voltages to control Coulomb blockade. All right, so now what we want to understand first is the charging energy in this system. Here it is. What we found here, eventually, this formula perhaps is difficult to derive. Well, I wouldn't say difficult, it's just a boring electrostatic problem which you have perhaps gotten during your electromagnetism course. Or perhaps you've been spared, I don't know. It's easy to understand. Capacitance here is a total capacitance of the system contributed by all capacitances to the island. And Q here is a discrete, continuous charge, which the gate wants to be present at this island. Here it is. It's a contribution of not only the gate, but also by if you apply voltage to the lead, this voltage also wants some charge to be stored in the island. Fine. So this is electrostatic energy, and I would like to compute energy difference. In this case, the energy difference, the energy which I have to pay if I would like to increase the number of electrons in the island by 1. Electrostatic energy. Here it is. Just take the difference of the squares. That's what I get. What's important for me to know that this is linear function of both number of electrons and induced charge, so that it's linear function of all voltages. Fine. Why do we care about energy differences? Because now we are going to transfer the electrons one by one from the lead to the island and back through left or right junction. And we are interested in energy costs associated with these transfers. Let us first understand that there are 4 possible electron transfers. And how can I get all this? The electrons can come to the island from the left or from the right, here and here. And they can go to the left or to the right, here and here. And right, if I go from the left or from the right, if electrons go from the left to the right, they increase the number of excess electrons. Otherwise, they decrease. So there are electrostatic energy changes associated with these processes. Oh, but look, I add something to this energy changes. What is this? Who can explain me? Or what did I add or subtract? These last terms, what do they mean? Change of energy in the source or drain. Yeah, it's energy change related, but it's not like, yeah. It is an energy of an electron which I have taken, for instance, in this case, from the left lead. or which I put to the left lid. Yeah, there's some potential associated with the lid, and that's also contributes to this. The point that electrons cannot disappear, right? I have to put it somewhere or extract it from somewhere. That's why electrostatic energy differences, they always come with the voltages of the lids where I put electrons or extract electrons. Fine, okay, I believe you understand this. Now how we can make use of this energy differences. Let me tell you, ladies and gentlemen, that if we are talking about spontaneous processes, that they go downhill. A stone rolls downhill, it won't roll uphill, right? So what does it mean? It means that if there's no disturbance from thermal fluctuations, these processes can only happen if the associated energy differences is negative. So the process happens, it dissipates and this energy somewhere, we don't care where, but it could not get energy. So if energy difference is positive, this process just doesn't happen. At least again at zero temperature. We'll talk about temperatures a little bit later. Good. And there are different transport regimes, I would say, associated with these energy differences. Transport regimes in single electron transistor. Most kind of fundamental interesting regime is Coulomb Blockade. In this case, there's absolutely no way to change the electron charge in the island, right? The transport is blocked, and it applies that all four differences for all four processes involved are larger than one. Sorry, larger than zero are positive. One has to pay energy. Another funny situation, it's one of the applications of this Coulomb Blockade devices. Let us rise the voltage of some electrode, for instance, left electrode. Then there is an opportunity for electron to come to the island. But right electrode is still at the same voltage, so electron can also escape to the right. And what does it mean for energy differences? All right, energy difference, this energy difference is negative, the process can happen. And tunneling to the right can happen as well. But let us understand that in this case, it's n+1 electron situation, right? We have this extra electron in the electron. So this energy difference is always negative. But funny enough, this energy difference is positive. What does it mean? It means that the electron which comes here blocks the transport for all other electrons which would also want to come. Okay, so would have to go here, and yeah, that's impossible. This energy difference is bigger than zero. Fine. Now is it time for the break? Yeah, perhaps. So let's have 8-minute break. We meet in 8 minutes. Meanwhile, I would stop the recording. Good. So let us go on with our lecture. Coulomb diamonds. First, about linguistics. In many languages, European or not, diamonds mean precious stones. So that's the title of the slide looks a little bit fancy. But as usual, English is a bit exceptional among other languages. So in this case, diamond means what in Dutch or in many other languages we would call a rhomb, geometrical figure of this shape. So that's what we mean by diamonds, and particular Coulomb diamonds. All right, let us see. We have 4 energy differences. Let me concentrate on some particular case of n equals 0, no excess electrons. Let me put all these 4 energy differences again for electrons coming from the left, from the right, going to the left, to the right. Let me put it just in the same row. And here I apply, for simplicity, it doesn't matter. I apply opposite voltage to the leads, just kind of, how can I say, choice of the ground point. Right, there's also this induced charge, which is contributed by, in this case, only by the gate electrode. And what I observe that all these conditions are lines in the plane of induced charge and transport voltage, right? They're lines because those are linear functions. Fine. So each condition is a line. So I put here 4 lines and see what I have. I have a region in this plane where all transport processes are blocked. It is a Coulomb Blockade diamond. Again, it's not precious stone. It is the rhomb. Right. If n is not 0, but say 1, basically we'll repeat everything, and we understand that this is just shift of this induced charge by 1. And so we plot, we put another diamond here. So hits 0, hits 1. Here it would be -1, and then it goes eventually on both sides. So there's a sequence of equal diamonds which are connected here at this point, where Coulomb blockade ceases even at 0 transport voltage. Coulomb diamonds. Let us see what I want to say. Basically, repeat what I have already said. If there is no temperature, then there is no current in these diamonds, in this Coulomb blockade efficiency. Fine. So that's just a diagram of these diamonds in the same line. And here there's a actual column map of current versus voltage, where you see there is almost no current over here in the diamonds, and some current which can be quite high otherwise. Counter question: is this experimental or theoretical picture? So, Francesca, why do you think it's theoretical? Lines seem very straight. Yes, yes, yes. It's precisely what is happening. It's too pretty to be experimental. Any experiment, especially in quantum transport, where people dealing with nanostructures in challenging conditions, would produce much more noisy data. Although ideally the lines would remain straight, it just would be much more disorder, much more stochastical experimental data around. Fine. Let us go into details of the description of the transport. Let us understand what we will need to describe transport. We have an L island which can be in a set of states, charge states, which are defined by intention number. It's important to understand, and it will be different in several lectures, that these states are not quantum states, and there can be no quantum coherence between them. Why is it so? Because if one looks at the details, let's look at the details. Let's have some electrons field and some empty levels to be filled. We can put this electron here or here. We remember that the level spacing is much smaller than Coulomb blockade energy, right? Eventually, it will be the same state, or we could even arrange an electron hole pair, so there will be no electron over here and electron over here. We can arrange the states for no energy cost, but all these quantum states will represent the same charge state. So that's why these states in this particular situation of normal metal just cannot be coherent, right? Which from one hand could be a bit disappointing, because we are in quantum transport, we expect quantum phenomena. From the other hand, it makes the description simple. In this case, we don't need to think about coherence between states as superpositions, and we can characterize what's going on just by probability to find the island in the state with a given n. Let's make a dynamical equation for this probability, which is called master equation. It doesn't, it applies not only to Coulomb blockade, it applies eventually to almost every phenomenon in this world, including whatever financial markets, what else? And the approach to this master equation is, in fact, very similar to bookkeeping. So for Coulomb blockade and for many other systems, you can just argue in very certain way and write down this master equation. Let us see probability. If the system goes from n to any other state, the probability is diminished. So there is a negative term in bookkeeping terms. In bookkeeping terms, it is outgoing term, expense term. Right? What is this? It first of all, in order to go from the state n, one has to be in state n. So we find here probability to be in state n. And then what states here is the total rate Okay, is the total rate of to go somewhere. In our case, it's contributed by all rates from when electrons tunnel to the junction and all rates to when electrons go out of the junction. Fine. Rate. Does this sound to you? You have heard about the rates probably in other courses. And I have a question to Dutch audience. How would you translate rate into Dutch? Just to make sure that we understand this. Do we have Dutchman in this course? Okay. Okay. Listen to me. Dit is waarschijnlijkheid per tijdseenheid. Which sounds rather long, but it is accurate, right? So the rate is a change of probability, not something, but something else, no coordinate, nor pressure, whatever. It's a change of probability per unit time. So the probability for some process to happen is proportional to time, right? And the coefficient of this probability is the rate. So in any case, rates have dimension frequency. Okay. Fine. So we know what the rates are, and I have the rates of all processes, and these are expense terms. Now we are talking about income in bookkeeping terms. What could be income? Initially, the state could be n-1. It comes with the same probability. And there can be a process where the system goes from n-1 to n. Okay, that's then when electrons come from the leads, right? And in this case, it's n-1. Initial state, it's n-1. Similar process if when electrons go to the leads, and initial state is n plus. Fine. So if we know the rates, we are in business. We can predict a probability to be in a certain state, right? What I put here is, here I only count rate from 2, but they also can come from the left and from the right, which is important if we compute the currents. Let us compute the currents. So again, we can get the currents if we know these probabilities. So the current through the left junction. Okay, it is in a certain state n, this probability Pn. Then again, the rates current is number of transfers per unit time. So I need to have the rates. Okay, and if electrons come from, they contribute to current with positive sign. If they go to the opposite direction, they contribute with minus sign. Good. The same I can write for right current. And I look at stationary conditions that it's clear that in stationary current conditions, both currents through left junction and through right junction must be the same. No charge would be accumulated. The problem is as follows. If I look at these two formulas, I don't recognize this property. They don't seem to be equal if I look at the formulas. Who can tell me why is it so? And why finally they are still equal? It is something from previous slide if you want a hint. It's complex. Right. This relation holds only for stationary current. So it will work if probabilities over here are solutions of stationary master equation. So I look at back. So stationary case, derivative is 0. There's some solution for these probabilities. And if I take stationary probabilities and substitute it here, yeah, the currents are the same. Fine, nice to know. It's also good foolproof condition. Right. What I want to say is that it says that we have computed at the moment stationary currents. It's not an instant current. Current is due to single electron transfers. If I look at left junctions, has spikes like this. And in right junction, if I count current in the same direction, there's somehow correlated spikes. And average current, wow, is somewhere here. We computed because it's easy to measure. It's DC currents which are measured. It would be difficult to follow all the spikes. Although it's possible if you look at the noise produced by electrons tunneling in Coulomb Blockade circuits. Fine. So now, if I'm not mistaken, it's time to look at the rates. And let us talk about tunneling in metals. First of all, let me forget about Coulomb Blockade. It will appear in the next slide. All right, let me recall what we had in first lecture. It's a concept of tunnel barrier and some potential electron wave which comes at energy which is smaller than the barrier height. Has some chance, and for tunnel barriers it's a tiny chance to transmit. Probability of transmission is 10 to the, yes, just very small. What is frequently used in technology? It's aluminum. It's a property of aluminum. It's a property of oxide which grows at aluminum. It turns out that, yeah, if you take, for instance, iron and expose it to oxygen, sooner or later, it all becomes rust. Actually, I don't know if in modern everyday life you can see it, but well, perhaps your parents told you. So iron exposed to air would become rusty and very quickly. It's not the case of aluminum. It's a marvelous material, and the early applications of aluminum, we are eventually exploited this fact. Oxidation of aluminum stops at very narrow oxide, at very thin oxide layer, just 15 nanometers thick. That makes it convenient to make tunnel barriers at aluminum base. Right, and for this native aluminum oxide with native thickness, transmission probability is something like 10 to the minus 6. Very good. First Coulomb Blockade systems have been made from aluminum because it's very convenient metal. Right, let us look at the current and let us estimate the rate of electron transfer for this situation. So first of all, it's a Landau formula. We apply difference of potentials. So here, red corresponds to field states. Violet corresponds to empty states. So in this particular energy strip, electrons from the left can tunnel to the right. Fine. How frequently? What is the rate of this process? We know the relation between current and voltage at the tunnel barriers. So it's a tunneling conductance which enters the game. Right, and the rate is the current divided by elementary charge. That's how many electrons per second go through this tunnel barrier. Fine, so what's important, we have associated the rate with the width of the strip energy strip available for tunneling. Electrons cannot go there because they're blocked. They cannot go there because there are no electrons. All transfers happen in this energy strip. Good, there is no Coulomb blockade yet, but well, we can just put it almost immediately if we will think what will happen with an electron which has tunneled into a Coulomb blockaded island, right? So, okay, it's here, it wants to come, it came. It has come. Right. It has to charge the island, and that costs energy, electrostatic energy. So that the kinetic energy of this electron should be correspondingly reduced. But if it's reduced too far, if it goes here, the process just wouldn't happen. It will be blocked. All right. So we figured out that the energy width available for tunneling is just reduced by electrostatic energy. And that gives us immediately, without whatever mathematical calculations, the formula for this rate in the presence of Coulomb blockade. Good, we're done. Now we understand what we need to substitute into this master equation. The parameters are eventually conductances of tunnel junctions, and yeah, the energy is voltage supplied. But I also want to mention something about temperature, which I also promised. Right, the tunneling rates in the presence of final temperature. It turns out that also in this case, let me jump to the answer, they are determined by energy differences and conductances. How to say that? It's not complex. We just consider the same process. We implement Fermi-Golden rule. We just consider the same tunnel process, taking into account how do you call it, filling factors of corresponding states. So electron comes to the lead. It goes to a state in the island which should not be blocked. That's why I have this blocking factor. The electron should find the empty space. And the difference between energies of electron initial state and final state is, as we discussed, charging energy. One has to pay charging energy for that. Good, so it's energy difference which we have discussed. So here's a formula for the rate. What does it mean? Let me compare cold case and warm case. So as we discussed, if temperature is 0, then the rates, the processes can only happen if corresponding energy difference is negative. That's what we see, and the rate, as we discussed, is proportional to the width of available energy strip. If we warm the system a bit, there can be also processes where kind of thermal, when energy comes from thermal fluctuation, so there will be processes also at positive energies. And also, it looks like there's extra rate owing to thermal fluctuations also for negative energies, energy differences. Good, so we can also implement temperature if we wish for these transport equations. So now let me, we have all elements. We have all elements to describe the transport in single electron transistor, and eventually in more complex Coulomb blockade systems. Now let us look at the manifestations, what we're gonna see. Our simplest manifestation, and it has been observed in early stage, and it's been observed in very many nanostructures at regular basis. So it is perhaps the most widespread, I shouldn't say phenomenon, most widespread experimental signature which one can see in quantum transport systems. Coulomb oscillations. So what we do, we measure conductance, just linear conductance, applying a small bias voltage. And what we see, if we change gate voltage, is a sequence of peaks, which are sharp at low temperatures, which become wider if we increase temperature. So what is going on? In this particular point of gate voltage, perhaps I can just superimpose it with diamond picture. If I take another axis, which is the voltage, the diamonds would look like this. So the position of the peaks correspond to crossings of the diamond, the common points. So in this point, the energies of two states with different number of electrons are almost the same. And even with a small voltage, you can organize a switching between these two energies. So the current will go on. Right, so the period which you observe in gate voltage is defined by elementary charge and capacitance between the gate, electrode, and the island. I didn't get the reason. Could you please repeat it again? Why the this is reduced? Okay. But eventually, what could illustrate it here? But let's go a couple of slides ago, right? Sure. Now I jump from a metal, from bulk metal, to another side. And at this side, I have the island, Coulomb blockaded island. If it were no island, if it were another electrode, after jump, I would just go at the same energy. That's what I had in previous transparency. But now it is impossible due to energy balance. Namely, if electron is here, the island is charged. The island is charged and Coulomb energy has been paid for this charge. That's why the electron which propagates after tunneling in the island has smaller kinetic energy. All right, that's why the energy, the width of the energy strip is reduced by by this quantity. Good. So, okay, another control question. Let me formulate it a little bit emotionally. Sometimes emotions help you to solve problems, sometimes not. Okay, suppose you have a good grant who just does, for instance, master thesis, and he actually measures something Coulomb Blockade, and he comes to you and shows the plots like this, and he says it's Coulomb Blockade. But if you look at the scale of vertical axis, you see something like inverse ohm for the scale of the peaks. All right, the question is, do you still have a friend? And if not, why? Yeah, it's conductors, it's inverse ohms. So somewhere here, he measures 1 inverse ohm. Okay, who has an opinion about this situation? I need to go quite some slides ago. Here. Yes, yes. Sasha got it right. So we estimate the typical resistance of anything where Coulomb blockade can happen is pretty high. It's 10 to the 4 ohm, right? So conductance doesn't match its 4 orders of magnitude apart. So most likely it is a wrong explanation, and your friend has no responsibility for his or her words. Fine. Let us see. Let me first check if I'm doing this time schedule. Oh, that's fine. Let me talk a little bit more about temperature dependence, because eventually it may be practical to some extent. Yeah, it is clear that at very large temperatures, these oscillations would disappear. Why it is clear? Because the temperature would be sufficiently high to make any charge configurations. And sooner or later, we restore just Ohm's law. Charging energy will not be of any importance. That will correspond to this black line at very high temperature. Let's look at it from the other end. From low temperatures. Then, okay, how one can figure out what would be the this. The Coulomb diamonds come together, remember this point. So temperature should be roughly this energy proportional to gate voltage. That's why the width of Coulomb peaks would be of the order of a temperature. So that's what is happening at low temperature. The peak is just narrow, then it becomes wide and wider, staying at the same height. Okay, then it will become like this. It will become even more flat. Yeah, because the peaks just overlap. They look at a slightly modulated line. What is funny, and perhaps one can explain me this fact just on the spot. The position of this line in conductance is roughly a factor of 2. It differs by roughly a factor of 2 from the position of high temperature line. So first they overlap, but then for some interval of temperature, just grow as almost flat line. So roughly it's a factor of 2.
Maybe it's because, and it's a wild guess, at a high temperature, I don't know if you can hear me because my internet's quite bad. Maybe I should better type it.
Whatever.
Hello? Let's try this way. So maybe at high temperature, the charge energy can always be overcome. So it's like when you have maybe additional channels because you don't have to go through the diamond or something, that you can directly go to. You can use all the Coulomb blockaded channels, so you don't have to worry about the discreteness on the Coulomb diamond itself.
That's right. But can you explain the factor of 2? I mean, here you also hardly see Coulomb blockade, but still there's a factor of 2 roughly a change. Okay, Sasha is right, sir. At high temperature, we expect no influence of Coulomb blockade. If I redraw again this diamonds, the energy scale would be, well, somewhere here. Many Coulomb blockades, many charging states will be available. At moderate temperature, mostly the transport will happen in this domain. Right? There's enough temperature for processes in this domain to happen. But in this domain, we still have Coulomb blockade for the second electron. So what happens? Electron comes and another electron cannot while it is in there. So it works a bit, and its actual term, it works a bit like a turnstile in, you know, if you've been to Paris and went to underground, they frequently have it. Also, one can see it here in the Netherlands sometimes. It's a turnstile. So electrons can go only one by one through the island. One by one, so the second electron is blocked. It gives roughly a factor of 2. All right, this is explanation. So although Coulomb blockade seemed to vanish, it is still there. And believe me or not, it is one of the most promising applications of thermal of Coulomb blockade systems. They make sensitive thermometers, very cheap ones, in this particular temperature range, because the whole conductance depends on temperature in this particular region. Very good. Let me talk about other manifestation. It is called Coulomb staircase. And in this case, I guess we better look at this picture. In this case, we look at the current, not versus gate voltage. There's also systems where it is impossible or very difficult to modulate gate voltage, but they're still Coulomb blockaded. So we don't look at the current versus gate voltage. We look at the current versus transport voltage. And what you see in this curve, let us just observe what is going on. We have singularities of the current. In this particular case, it looks like current jumps, which are separated by rather regular intervals, and they actually come in series of jumps. So how to explain this? Let us draw again the series of Coulomb diamonds. So here we have diamonds, say, with 0 and 1. If we go further, we will have a diamond where both 0 and 1 can occur. If we go further in voltage, there's also a region where you can have 0, 1, and also, guess what? Also -1. It's quite obvious scheme. Good. And we will look at it at a given transport voltage. So transport voltage is here, which is a line. And okay, we see that. We see regular crossings with the boundaries of higher order diamonds. So there are some values, special values of voltage. They depend on the induced charge as well, where a new charge state at zero temperature comes into play. Fine. It has to be said that kind of the degree of manifestation of this effect depends on conductance. If the conductances of two junctions are equal, I believe you can see something, but well, without pointing arrows, you probably would not see anything. So this Coulomb staircase is not very much pronounced. But there are also systems where these junctions differ by a large. And I guess in this case, I took what was that? I guess it was factor of 50 between the junctions. Right, one can see very pronounced features in the current. Again, also another way to observe manifestations of Coulomb blockade. In this case, you need to have strongly unequal conductances. Right, so now I want to take to talk about something. Oh, I'm almost out of time. About something fancy. Okay, I will keep it short. For tunneling, general philosophical scheme. Quantum mechanics and classical physics, to some extent, looks as authoritarian society, almost dictatorship. The positions and the histories of all particles are predetermined by some general laws imposed, and seems to be no freedom at all. Quantum mechanics corresponds to, I would say, modern democracy. It's not anarchy. The particles cannot do whatever they want, right? There are some general laws like energy conservation, particle conservation, and it seems to be impossible to break these laws. Otherwise, quantum particles can do whatever they want. And if there's any possibility to do this, they surely would do so. Good. Let's get it straight to Coulomb blockade systems. Let me consider Coulomb blockade. What does it mean? It means that if I want to put an electron to the island in this particular situation, I have to pay energy, and I don't have it. If I'm an electron, I couldn't afford to go to the island. But if I can cooperate with another electron, I could go around this whatever stupid law prohibition. I could cheat. Well, it's not cheating of energy conservation, it's cheating this Coulomb barrier. Look how the electrons can cheat this. Electron comes here, and at the same time, another electron leaves. Then, overall, there is no charge change. There's no energy to be paid. Right? So this process is allowed. And the charge is transferred. That's how core tunneling works. So it's cooperative tunneling of two electrons, or there could be even more complex processes where many electrons tunnel simultaneously. How one can estimate the rate of this process? I kind of put many formulas in this transparency, but it's something for advanced quantum mechanics, of course. Let me give a simple estimation. This electron, okay, suppose an electron, I would try to check if energy conservation works. Right, I kind of can try to tunnel to the island, and I can stay over there only for a little time which is allowed by energy conservation. So that gives me a probability of such process. I'm tunneling with a rate gamma, and it is It gives me a probability, right? Instead of delta t, I should put delta E divided by h bar. So with this probability, I will have an electron through the left junction, kind of picking around, trying to cheat energy conservation. And if an electron, another electron tunnels, it does it with a rate, yeah, let me call it gamma r. So it gives me eventually very relevant estimation for the rate. The total rate is a product of the rates of individual electrons divided by energy difference, Coulomb energy difference. So it's smaller than the usual rate, but it persists with no, it persists on also if a single electron tunnel is suppressed. That's why it's important. So let me quickly flash the formulas. So there can be a rate, even in Coulomb blockade, which is proportional to third power of voltage. So eventually within the blockade, current is taken cation into account. It looks like that. So for single electron tunnel is suppressed up to certain threshold. Here, catunneling happens. 2 electron catunnelings. Somewhere near threshold, you cannot distinguish processes of cooperative tunneling of 2 electrons and subsequent tunneling of 2 electrons. So precisely at the threshold, it has to be something else. Right. So it gives you the notion of what is going in the Coulomb diamond if higher order quantum processes are taken into account. I think my time is up. Thank you for your attention. I will stop the